Hi, it's David from Electric Teaching, and we are going to try to determine the area between functions using integration. The area is bounded by f of x squared plus 1, so this is a parabola up 1, and g of x is equal to 5, so this is y equals 5, so this is where every y coordinate is 5, so that's a horizontal line. And x equals 0, so that's where x equals 0, which is the y-axis. So let's take a quick look at what these functions look like. X squared plus 1 will be a parabola that'll look something towards this. And then it has symmetry on the other side. And we have g of x equal 5. So we got parabola up 1 and we got horizontal line equal equal 5. 1, 2, 3, 4, 5. Okay. And it looks like, if I drew my parabola correctly, that we have an intersection at 2. We have the exact same y coordinates at 2. Plug and chug a 2. And you'll see that f of x, f of 2 is equal to 5. So that we do have an intersection point. That's going to be important to know. You always need to know where the intersections are. X equals 0, as we said, is the horizontal line of the y-axis. This is where every coordinate is equal to, has an x ordinate of 0. So the bounded area between these curves, I guess has a left side and a right side. But what I want to do is I really want to focus on the right side. I want to focus on the right side right now. You can see there's symmetry. So if you really wanted the whole area bounded by the line of 5 and the parabola, you could simply double what we're going to do. What I want to focus on is trying to get this area, Okay, so I'm looking at trying to fill in this area with and determine how big it is. So the way you want to look at this with area between curves is always the top function minus the bottom function. Okay, and this is going to be integration of each. If I integrate the top function, you could see, if you know your integration well, you would get this box, which clearly is a 2 by 5 box. So that is an area of 10. So the inside area, the integration of just the line itself, is 10. Okay, if I integrate the parabola, okay, I would get the area inside here. And inside here, if I get this area, okay, and let's say, I don't know what it is, but let's say, looking at it, 1, 2, 3, 4, maybe about 4 or 5. If I subtract off that area of maybe 4 or 5, okay, then I would be leaving the remaining area that we're looking for, which is this area. So this is why the top function integration in yellow, making a total of 10, okay, minus the bottom integration, maybe it's about 4 or 5, so I would subtract that off and it would leave the purple area. So that's the concept behind top function minus bottom function. And it's important to realize that it actually works below the x-axis as well. Because if you subtract off the top function, which is a smaller negative, minus a bigger negative, the integration of the bottom function, remember integrations are negative when they're below the x-axis, then you would still end up with a positive area. An area should always be positive when we're specifically talking about area bounded by curves. So that's a quick explanation of what we're doing here. Now I'm going to try to run through the actual mechanics of it. Excuse me, running a little bit of a cold. Okay, we got integration of x squared plus 1. Okay, top function is the 5 line. Let's be careful here. So we're going to integrate 5. We're going to integrate 5 dx. And then we're going to subtract off the integration of x squared plus 1 dx. So if we do this, we will be left with the purple area. So our area then will be the top integration minus the bottom integration. We're running this from, let's see, xy's 0, that's the starting point, all the way through to x equaled 2. So these are 0 to 2. The actual formula you'll see in the book will properly pull out the integration symbol and leave it one function minus the other. One function minus the other. And that's important to realize, that basic integration, summing up tricks, so basic summing rules. I'm going to sum up these rectangles in a sense, infinite rectangles, which is the basis and understanding of integration. Let's do the math. 0, 2, collect like terms. Okay, got to be really careful here. I didn't notate that well. Almost made a really important and common mistake. Negative distribution. Really important here. I'm going to have a negative x squared, a negative x squared, excuse me, and a 5 minus 1. A 5 minus 1, so a positive 4. The integration will look like this then. We're going to add 1, flip and multiply as I try to teach my students to quickly do it. Okay, add an x to any constant. Running this, plugging and chugging this from 0 to 2, so plug and chug the 2 first. 2 first is then a minus 8 thirds plus a 8. And if I go to subtract off the plug and chug of 0, you're going to see that I'm going to subtract off 0, because that's going to be a value of 0 at x equals 0. Final answer then is 8 minus 8 thirds. 8 minus 8 thirds. Okay, so 8 thirds, that goes in what, 2 and 2/3 time, is that correct? 2 and 2/3 time. So let's subtract off 2 and then subtract off the 2/3 to quickly do this without the aid of a calculator. I hope you're not grabbing a calculator when you see these kind of problems. So 8 minus 2 is 6, but then we subtract off another 2/3 and we're going to get 5 1/3. 5 1/3. Double check. If you add them together, you do get 8. We're looking good. The area in purple, the area in purple right up here, this area will be 5 1/3. We estimated that the blue area below was around 4 or 5. If we subtract it off, you can just count the squares, little basic geometry trick. Okay, and they look like they were going to be between 4 and 5, and seems we were accurate because our answer ended up being 5 1/3, leaving 4 2/3 for the blue area. Okay, my name's David from Electroteaching. This is part 1. I'm going to do part 2 next, where we're going to take a look at a slightly more difficult problem, where we're going to look at the area bounded between a cubic and a linear. I hope that I have helped.